In the decimal system, there are values ranging from 0 to 9, giving 10 possible numbers. If a larger number is required, then another column is added. The value of the numbers in the next column to the left are 10 times the value of the ones on the right. The units column has a value of 1, the tens column has a value of 10, the hundreds column has a value of 100, etc. Consider the number 4,852. It consists of 4 thousands plus 8 hundreds plus 5 tens plus 2 ones, giving us 4,852. The subscript 10 indicates that this is the base 10 numbering system. Consider a binary system where there are only two values, 0 and 1. The columns to the left have a value that is twice the value of the ones to its right. There's the units column that has a value of 1, there's the twos column that has a value of 2, the fours column that has a value of 4, and so on. Consider the binary number 1011. There is 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1, giving a total of 11 decimal. The subscript 2 indicates that the number has the base 2 or binary number system. Binary can be a bit cumbersome when dealing with large numbers, so the hexadecimal number system was found to be useful. 4 binary digits are grouped together and we see that there are 16 values, 0 to 15. Starting with the unit column, each column to the left is 16 times more than the one on the right. With the hexadecimal number system, we have digits 0 to 9, and for values 10 to 15, we use the digits A, B, C, D, E, and F. Consider the hexadecimal number B7F. The subscript H tells us that it is a hexadecimal number from the base 16 numbering system. The number B represents 11 times 256, which equals 2,816, plus 7 times 16, which equals 112, plus 15 times 1, which gives us a total of 2,943. The smallest element in a computer is the binary digit, which was quickly shortened to the term bit. A bit can be either on or off. By itself, a bit doesn't contain much information. In the computer memory, 8 bits are grouped together to form 1 byte of memory. Note, the bits are numbered from 0 to 7. In computing, you will see objects numbered from 0. To work out the total number of possibilities, raise the power of 2 by the number of bits. So 2 to the power of 8 is 256. There are 256 possible values ranging from 0 to 255. The bit on the right is the least significant bit because it has a value of 1. The bit on the left is the most significant bit because it has a value of 128. An integer is a whole number. Our byte of memory can store integer values from 0 to 255. Generally, 2 bytes are used to store integers in computers. Our integer is a 16-bit number, and the value of the least significant bit is still 1, and the most significant bit has a value of 32,767. Numbers can have a range of 0 to 65,535. The standard 16-bit integer is just positive numbers. However, negative numbers are required. The most significant bit was changed to become a sign bit. If the sign bit is 0, then the numbers are positive. If the sign bit is 1, then the numbers are negative. Consider this number that has a 0 in the most significant bit, and the rest of the numbers are 1. This will have a value of positive 32,767. You can check this by adding the values of 2 to the power of 0 plus 2 to the power of 1, etc. to 2 to the power of 14. Let's add 1 to the number. The number now has a 1 in the most significant bit. That means that it is a negative number. The number is a 1 with 15 zeros, so the value is minus 32,768. If another 1 is added, then the number is minus 32,768 plus 1, so the value is minus 32,767. The default status for integer numbers is that they are signed integers, and for a 16-bit number the range of values is 32,767 to minus 32,768. Some PLCs allow you to create an unsigned integer. Some PLCs allow storage of larger numbers. 4 bytes are used, giving a total of 32 bits. This gives us a range of plus or minus 2 billion. PLC analog cards converts the analog values to counts, so a range of 0 to 100% could be converted to 0 to 10,000 counts. Even though there isn't a decimal place, the decimal place will be assumed to be at least 2 digits, so 10,000 counts would be interpreted as 100.00%. So 6,547 counts would be interpreted as 65.47%. Real numbers are stored in PLCs in scientific notation format, where the number consists of one whole number followed by a decimal point and the rest of the numbers, multiplied by an exponent to the power of 10. The number can be positive or negative, and the exponent can be positive or negative. Generally, if a PLC has the ability to store real numbers, then they use 32 bits of data or 4 bytes. A computer may require 64 bits to perform more precise calculations. A PLC takes the analog value and converts the values to counts. The scaling function allows the conversion of a range of values to another range. It would be more useful to display the tank level in litres rather than counts. The graph shows 0 to 10,000 counts being scaled to 0 to 5 litres tank level. PLC manufacturers differ in how the scaling functions work. Schneider's Unity Pro software have a scaling function that you specify the input min, input max, output min, and output max. The scaling function performs the scaling calculation. The Zelio PLC input has 9.9 volts, and the input card converts this to 1023 counts. The gain function block provides the scaling. At this point, the gain is set to 1 to 1. Our aim is to use the gain control to provide a range of numbers that equate to the tank level of 0 to 5 litres. Open the gain parameters. The screen opens and the default values for the ratio of input to output is 1 to 1. The values must be integers, so no decimal places. The horizontal scale or denominator is 1023 and the vertical scale or numerator is 5. The device will scale from 0 to 5 litres. There is a problem in that the scaled output will only be in 1 litre increments. This resolution would be unacceptable. Better resolution can be achieved if the numerator value is changed from 5 to 500. That means that the 1023 steps are changed to 500 steps. This will effectively provide 2 decimal places of resolution. The industrial process can be measured using a measuring device. The measuring device provides a signal to the controller, which can be a PLC. The controller sends a signal to the control device that controls the process. The PLC will also be able to accept a value that the operator can choose that the process is required to achieve. This is known as the set point. Previously, the way PLC stores numbers was discussed. In particular, signed integers were discussed. When a PLC has a number that has gone above 32,767, then the number is treated as a negative number. This could be catastrophic if the number is being used for controlling a process. The jump to a negative number could cause a problem. The PLC has an overflow flag that comes on if the calculation extends outside acceptable values. The overflow may result in a PLC fault that will stop the operation of the PLC. Otherwise, the program will need to be tested to determine if an overflow is possible and then the overflow prevented.